Okay, it's a big pleasure to announce Daniel Litt from University of Toronto. He will tell us about the converse to Eisenstein's last student.
Thank you for the introduction. It's nice to be here. Before I start, let me say this is meant to be kind of an accessible talk. I know not everyone in the audience is like an arithmetic geometer, so feel free to ask questions and just interrupt me at any time. So let me start with kind of the motivating question of the talk, which I think was really one of the animating questions of like the second half of 19th century mathematics. So maybe in this generality, the first place I was able to find it in print was in a paper of Fuchs from 1975, which is, so how do you recognize when an algebraic differential equation, when does an algebraic differential equation have solutions which are algebraic functions? So say algebraic solutions, so I mean solutions which satisfy a polynomial whose coefficients are rational functions.
And do you mean all solutions in algebraic, or do you mean there exist in algebraic?
I mean there exists an algebraic solution, and since I'm going to be talking about not just linear differential equations, it's really a crucial difference. It's a good question. Okay, so let me just do maybe an example to show you that this is sort of a subtle question. So this is maybe the first differential equation to write down. So d dz minus a over z f of z is 0, and here a is some fixed complex number. So this has, well, okay, what are the solutions to this differential equation? All right, sorry for making you do homework. So the solution is constant times z to the a, and these are algebraic. Exactly when a is a rational number. So to see that, well, it's kind of clear they're algebraic. If a is rational, they're the roots of the function z. And if a is irrational, then they're not even finitely branching. So they can't be algebraic. Okay, but this should, maybe this should justify why I'm giving this talk in an arithmetic geometry seminar. This is an arithmetic condition. Okay, so by now I think there's a pretty standard conjectural answer to this question for linear differential equations due to Grothendieck-Katz. So let me just recall some simple form of that. And, I'm not sure exactly about the history. I'm sure there are people in the audience who know much more about it than I do, but my understanding is that maybe Grothendieck never wrote anything about it. Katz sort of wrote the first papers about it and proved the first important results on this conjecture, and I'll recall some of those soon. So let me state the conjecture in kind of a simple form, so that all the solutions to the differential equation d dz minus a f of z equals 0 are algebraic. And here A will be a matrix, R matrix of rational functions with rational coefficients. And so F is a vector of holomorphic functions, if you like. And the conjecture is that all of the solutions to this differential equation are algebraic if and only if some arithmetic condition is satisfied. So d dz minus a, so this differential operator to the pth power is identically 0 mod p for almost all primes p. Say a word about what that means. So here A is a matrix of rational functions with rational coefficients, so it makes sense to reduce it mod p for almost all p. So this is a differential operator which you can apply to polynomials mod p, and then you ask, as a differential operator acting on polynomials mod p, is it identically 0 mod p? Okay, so of course, if you look in Katz, you'll see that there's a much more general formulation of this conjecture which specializes to this when the base variety is an open subset of the affine line over Q. But in fact, I think this conjecture is equivalent to general statement. Okay, maybe let me just say a word because it will show up later about where this comes from. One way to think about this is that if you write down a formal Taylor series expansion of a solution to this differential equation, this will show up in the pth term, the Taylor series expansions. So something about whether the pth term has a p appearing in the denominator. Okay, So what's known? Not much. So let me say a few words about the known cases. So I think the first and arguably the most important case where we know that this conjecture has a positive answer is the case of Picard-Fuchs equations, Gauss-Monod connections. And this is Grothendieck-Katz in 1972. So here, these are differential equations which control the cohomology of a family of smooth projective varieties over your base here, over an open subset of the affine line. And I'll return to the formal definition much later. For the experts, maybe let me just remark. So you could ask, do we know the conjecture for some ends of Gauss-Monod connections, or some ends of Picard-Fuchs equations? And I think the answer is no. Even for such things, we don't know. Okay, so the other main case in which this conjecture is known is the case of solvable monodromy. So for example, if this matrix A is upper triangular, and I'm not 100% sure about the chronology here, but I think, so the first case of rank 1 was done by the Chudnovskys, and then their methods were generalized to handle this case by Vogt and Andre. And there's a few there's quite a bit of beautiful work on this conjecture beyond these two cases. Let me just mention some names: Yun Xing Teng, Anant Shankar, and Grothendieck have all proven cases of this conjecture. But I think maybe these are, at least in my view, the most important cases where the conjecture is known. Okay, I mean, of course, it would be very interesting to say something about this conjecture, but for me, the starting point of this talk was to try to understand what a good statement would be for nonlinear differential equations. And so there already is some variant of the P-curvature conjecture for nonlinear differential equations due to, maybe let me just mention the name. So the nonlinear case, there's a conjecture which generalizes this one of Eck et al. Shepard, Barron, and Taylor. I think it's an unpublished work. Very little is known about it. And it's a conjecture about when all solutions to a nonlinear differential equation are algebraic. And at least in my view, that's sort of not a good answer to this question. So if you have a nonlinear differential equation, it can really have a few sporadic solutions. And I think some people in this room, for example, algebraic, are very interested in understanding sort of sporadic algebraic solutions to nonlinear differential equations, like the Campbell-Basics equation, or some other nonlinear differential equations that show up in algebraic geometry and that I hope to convince you to care about by the end of this. So for me, this was.
They wrote nothing?
I'm sorry?
There's nothing written?
There's some kind of, if you email them, you can get a paper. I'm sorry?
That instead.
Yeah, so I emailed Shepard Barron. But yeah, as far as I know, I can say what the conjecture is. So they're working in the setting of a foliation, like an integrable foliation, and the conjecture is that if it's closed under Pth powers mod P from P, then all the loops should be algebraic. Okay, so the question for me is, well, what about nonlinear ODE? Okay, so if you are trying to answer this question, you maybe want to look for some properties algebraic functions have that the general solutions to differential equations do not have. And here's one. So this is a theorem of Eisenstein. It appeared in his final paper, written in 1852. So let me state some version of it. So suppose you have a power series, f of z, the sum of an z to the n, power series with rational coefficients, and suppose it's algebraic over the field of rational functions, so meaning it satisfies a polynomial whose coefficients are rational functions. Then there exists some integer n such that all the Taylor coefficients lie in z adjoin 1 over n. So in other words, only finitely many primes divide the denominators of these rational numbers. Okay, so this is, I'm calling this Eisenstein's last theorem because it appeared in the last paper he ever wrote. So a little 3-page note where he states this theorem. He gives sort of a one-line sketch of the proof, which was eventually fleshed out by Heimann in, I think, 1854, maybe. And then he says something like, I found some amazing applications of this theorem to the theory of algebraic differential equations, which will appear in future work. And then he died of tuberculosis at the age of 29. So there's sort of a little mystery there. It would be very interesting if one could figure out what applications he had in mind. Okay, so if you look at any book which mentions this theorem, it will tell you the converse to this theorem is false, and that's kind of obvious. There's plenty of algebraic functions, of non-algebraic functions whose Taylor extensions have this property. There's uncountably many power series with this property, but uncountably many rational functions. And if you work a little bit harder, you'll see there's even counterexamples which are solutions to differential equations. So I'll give you an example. Okay, so the talk is over. The converse to this theorem is false. No, but I'll try to make sense of a reasonable converse to this theorem. Okay, so let's look at some examples before I do that. So here's a function which is famously not algebraic, e to the z, and it looks like the sum of z to the n for n factorial. Okay, and well, infinitely many primes divide these numbers because there are infinitely many prime numbers by a theorem of Euclid. Okay, so this is an example of a non-algebraic function, and you can see that it's not algebraic using this theorem, for example. Okay, maybe let me just give you an algebraic example to show you a bit about how this works. So if you take the square root of 1 plus z, this looks like the sum of 1/2 choose n, z to the n, and you can see, for example, from like the p-adic continuity of binomial coefficients, that these coefficients only have powers of 2 in the denominator. Okay, so this is an example where you have an algebraic function and you only see powers of 1 prime in the denominator. Okay, let me give you a more fun example. Maybe let me call this a non-example. It's a non-algebraic function that satisfies the conclusion of this theorem of Eisenstein. So if you take 1 over pi times the integral from 0 to 1 of dx over the square root of x times 1 minus x times 1 minus zx. So this is a function of z. Let me tell you its Taylor series expansion. It's the sum of 2k choose k squared times z over 16 to the k. Okay, well, this is an integer. Here you only see its powers of 2. So this definitely satisfies the conclusion of the theorem, but it's not hard to see this is not an algebraic function. It's an elliptic integral. It's not finitely branching. Okay, not only is it not an algebraic function, it also satisfies a linear differential equation. I mean, it's an integral. It's kind of clear that it's a linear differential equation. That's even a Picard-Fuchs equation. Okay. And if you stare at this for a second, you'll see that this differential equation has a singularity at z equals 0. Okay. And if you start looking at examples, you see all the examples of this property, at least all the examples I know of the property. The differential equation ends up having like where you have a non-algebraic function whose Taylor series expansion has this property and satisfies the differential equation is singular at 0. Okay, so with that in mind, let me make a conjecture. So this is supposed to be the converse to this theorem of Eisenstein, or a converse to this theorem of Eisenstein. So suppose what is a power series f of z is sum of an z to the n. This is a power series with rational coefficients, and it satisfies possibly nonlinear differential equation. So I'm gonna state a special case first of this flavor, and then I'll reformulate it in more geometric language. So here it's the special case. This is kind of a fairly special kind of nonlinear differential equation, where here f is a rational function and z in y0 through yn minus 1. I've written it this way, so there's just one fn on the left here, so to guarantee that there's always Taylor series expansions of solutions. So to write such a thing down, you're kind of solving some recursion relation for the coefficients. And then I told you I need the differential equation to be non-singular at 0. So what does that mean? So that means that this capital F is defined at the initial condition. So that's 0, f of 0, f prime of 0, all the way up to n minus 1 of 0. So I want this to be defined. Let me just be really explicit about what I mean by that. This is the ratio of two polynomials, and I would like the denominator to not vanish at this point. So then the conjecture is that the following are equivalent. So first of all, f is algebraic over Q of Z to the conclusion of Eisenstein's theorem holds. So there exists some positive n such that all the coefficients of this Taylor series lie in Z adjoin 1 over n. So this is only, again, this is what does it mean? It means only finitely many primes divide the denominators here. Okay, let me make that. So I'm going to call this condition integrality of the power series. And then there's a strong form of integrality that I want to write down just so that I'm including the P-curvature conjecture in this statement. So there exists some function from primes to non-negative integers with two properties. So first of all, the limit of this function, omega of p divided by p, as p goes to infinity, is infinite. So omega goes faster than any constant multiple of p. So think omega is p log of p, or p log of p, or p log of p, something like that. And then it should have the following property, which is that if you look at the first omega terms of this Taylor series, they don't have p's in the denominator. Okay. So let me briefly discuss this. Okay, so 1 implies 2 is Eisenstein's theorem, 2 implies 3 is trivial, and then any backwards direction is hard. Okay, what's the relationship to the P-curvature conjecture? So let me make a couple of remarks here. So the hypothesis of the P-curvature conjecture, if you stare at Taylor's formula, tells you that 3 holds with omega something like p squared, maybe p squared minus 1. So the first p squared minus 1 terms don't have p's in the denominator. And that's not true just for one solution, it's true for all solutions to the differential equation, Taylor expanded at any. Okay, and here the hypothesis is just that for one solution expanded at about 1 point, the Taylor expansion has this integrality property. So the hypothesis is much weaker than the P-curvature conjecture, so the conjecture is much stronger. So first thing is that it implies classical P-curvature conjecture.
And in condition 3, how many p's is this supposed to be true for?
Sorry, almost all. I think, and somehow, maybe if I allowed a -1 here or something, it'd be automatic. The fact that I haven't specified omega.
Do you think if you, about the whatever apply, would you, if you knew it in density 1 instead of almost all, you think it should still be true?
I would guess, but I mean, I'm guessing something about a conjecture where I have very little evidence. I'll tell you the evidence I have for this. And the point of this talk will be to give evidence for this conjecture. So it implies P-curvature conjecture. I think it's much stronger than P-curvature conjecture. So if I have time, I'll try to say it makes some predictions about linear differential equations that seem to be true in examples and which I don't seem to follow from the classical P-curvature conjecture. So maybe let me just say, so for linear ODE, I've seen some variant of the equivalence between 1 and 2 attributed to Andre and Kristol. I'm a little hesitant to make that attribution myself because I don't think they've written anything explicitly making this conjecture, but they're clearly thinking along related lines. Okay. Okay, so what's the goal of this talk? I'm definitely not going to prove this conjecture, but I want to try to explain some special cases I can prove both for linear ODE and then also for nonlinear differential equations. So I really want to prove that some solutions to nonlinear differential equations are algebraic from this kind of
So when you say one variant of one is equivalent to two. Do you mean they claim to prove it or
Oh, no, they've just, it's been attributed to them as a conjecture.
as a,
Yeah. So there's, I think there's some paper of Andre where he says something like, it is natural to consider the following as a variant of a conjecture if we stole one. It's not exactly one implies two, but it's something. Okay, any questions about the conjecture?
So in Eisenstein's work, was there any mention of differential equations?
Yeah, so he says something like, I found some great applications of this theorem for the theory of differential equations. They'll appear in a future work. But yeah, but he doesn't say what those applications were. It's really, it's kind of tantalizing. If you ask me after the talk, I can tell you my guess as to what he was doing. So somehow in the air was the study of which hypergeometric functions are algebraic. And my guess is that he was thinking about it along those lines. Okay. Okay, so before I start telling you results, I want to reformulate the conjecture in sort of more algebra geometric language. So let me say what I mean by a differential equation. What is a differential equation? Okay, so for me, a differential equation will mean a horizontal integrable foliation. So let me say what that is. So here, m to s over c will be a smooth morphism of smooth schemes. At the very end of the talk, I'll slightly relax the word smooth and the word schemes. And then let me make a definition. So an integrable foliation on m over s is so I'm never going to say the word integrable again. For me, all foliations in this talk will be integrable. Is a subsheaf f inside of the tangent sheaf of m, such that two conditions hold. So first of all, one, the tangent sheaf is a sheaf of Lie algebras. If you take two vector fields, you can take the commutator. That's a new vector field, and I want f to be closed under that Lie bracket. So that's what it means to be integrable. So I apologize, I did say integrable again. And then second of all, I want this to kind of split the tangent exact sequence for pi. So I want the following composition. So f includes into Tm, and then this maps to I star of Ts via the derivative of pi, and I want this to be an isomorphism. Okay, so the picture you should have in mind is here's m, here's s, and then locally you're writing m as a union, analytically locally, sorry, you're writing m as a union of sections to this map. So in other words, you're writing the tangent space, temporary point of m as the tangent space of the fiber plus the tangent space of the base. Okay, so for me, this is what a differential equation will be. I'll give you some examples.
what's an isomorphism?
Sorry, this composition, so f includes into the tangent bundle maps to pi opposite. Yes. Great. Okay, so let me say what a solution to a differential equation is. So it would be a leaf of the foliation. So a leaf of f is a smooth formal scheme Z mapping the total space of M such that the following holds. So first of all, there's a map from tangent sheaf to Z to pullback of the tangent sheaf to M. Inside of here is the pullback of the foliation. And I want, first of all, the map to factor like this. And then second of all, I want this to be an isomorphism. So in other words, Z is a possibly formal subscheme whose tangent sheaf is the foliation, it's tangent to the foliation. Okay. So maybe the remark is that formal or even complex analytic leaves exist through every point. of M. So this is, I guess, the theorem of Frobenius, whose proof is the theory of Taylor series. And then the question is, well, when is there a leaf, which is also an algebraic variety? Are there any questions about this? Go ahead. So let me restate the conjecture in this language. Okay, so the conjecture is so fix some point M and M. So we're in the setting over here where we're given a horizontal foliation on M of S. And pick a point of M, and then the conjecture is that the following are equivalent. So one, there exists an algebraic leaf through this point. Two, so you can spread out the whole situation. So at the point little m, the space capital M, capital S, pi, and F descend to a finitely generated Z-algebra R, and there exists a formal leaf from spoof R brackets x1 through x to mass rather through N. So what does this really mean? It means that if you write out the formal leaf over C in terms of power series, the coefficients of those power series lie in a finitely generated Z-algebra. That's all that means. So really the same condition from before. If you think finitely generated Z subalgebras of Q are Z adjoint 1 over N for some N. Okay, and then 3, I had this condition about some rapidly growing function omega of P, and I will just say there's a version of that in this case, which I don't want to write on the board. If you ask me after the talk, I can tell you what it is. Not horrible. Maybe let me give these things names. So this is the leaf being algebraic. This is the formal leaf being integral. And then this is something I'll call omega p integral. So morally, you should think the first omega p coefficients, pi and z, localized for p. Okay. So let me give you some examples of foliations where I can say something. Are there any questions about the conjecture before I do that? So here, let me just give you an example of some horizontal foliations. So complex analytically, they'll all have the following shape. I'm going to set S tilde be the universal cover of S, and then I'm going to have an action of pi 1 of S on V, where V is some complex analytic space. It's like a smooth complex manifold, or that won't always be the case. Okay, and then what's my space M going to be? I'm going to take M to be S tilde times V divided out by the diagonal action of pi 1 of S. Here, pi 1 of S acts on the universal cover by Det transformations and on V by the specified action. This maps to S via just projection to the first factor. And I'm going to take F to be the natural descent of the pullback of the tangent bundle S tilde. So if you think here, this thing is a square, it obviously has some kind of decomposition. The tangent bundle obviously has some decomposition into S tilde directions and V directions, and the S tilde directions descend to something on this equation. Okay, so all my examples will have this flavor. Let me explain what V will be. Suppose I'm given a smooth proper morphism x to s, and there's a famous linear differential equation, Gauss-Model connection, one can associate to this. So I'm going to fix a point little s and s, and I will set V to be the cohomology of the fiber. So I'm going to take S tilde times the cohomology of the fiber, complex coefficients, modulo pi1 of the base. This acts on S tilde by deck transformations and the cohomology of the fiber via the monodromy representation. This maps to S. Okay, it's not at all obvious. This is some kind of algebraic foliation. Let me just describe it a little bit more algebraically. So if you want to think of this, well, if you know what an Ehresmann connection is, this is an Ehresmann connection. If you translate to the world of flat vector bundles, you get the following thing. You get the local system, RIF over star C, which collects together the cohomology of the fibers, tensored with O, with the natural connection identity tensor D. And this is the same as the following algebraic gadget. So you take the de Rham complex of X over S, you push it forward through F, and then you take the Gauss-Model connection, and this was shown to be algebraic by Katz and Oda. This is sort of an algebraic description of this complex analytic space with the foliation I described there. Okay, so this is an algebraic differential equation in my sense. And then I want to give a non-abelian version of the same story. So this is where the nonlinear ODE come into this. So again, I have some x to f, x to s, smooth proper. If you'd like, you can equip x with a relative SNC divisor, and everything I'm going to say, including the main results of this talk, will be true. But I'm not going to do that right now, just for simplicity. So now I'm going to take s tilde, and what am I going to multiply it by? So instead of taking cohomology, I'm going to look at the space of representations of the fundamental group of a fiber. I'm going to take com from pi1 the fiber into, let's say, SLR C. It doesn't really matter what I put here, up to conjugacy. And then I'm going to mod out by the action of pi1 of S. So here again, that's on S tilde by deck transformations. Here, how does it act? Well, there's an outer action of pi1 of the base on pi1 of the fiber. If you put a loop in the fiber, you can drag it around a loop in the base, you get a new loop in the fiber. This gives a action of pi1 of the base on conjugacy classes of representation. Okay. This maps to S. Okay, at least where this is smooth, this defines a foliation. Not a priori algebraic. In this case where this is smooth and proper, write that. Simpson gives a more algebraic description of this foliation. So he shows this is, you can think of the M de Rham of X over S. So this is the moduli space, moduli stack of flat connections on X over S. Okay, at least on the smooth locus, there is some natural isomonodromy foliation. I'll say a word about that in a second. Let me just say in general, this thing is a crystal over S. So that's a way of saying what a foliation is without requiring smoothness. And I'm not going to say anything more about that, but if you want me to after the talk, I'm going to do so. Okay, so let me just say what are, in this language, what are the leaves of this foliation? So a map to this thing is a family of flat connections on the fibers of X over S, and it's a leaf if the monodromy representations associated with those connections are locally constant. The fibers of X over S are all homotopy equivalent to each other. This is the smooth proper math. So it makes sense if you have a local system on two nearby fibers to ask if it's the same local system. Okay, so this is an example of a nonlinear differential equation, and I'll give you some examples of it. Shortly, these things have been really studied since the beginning of the 20th century. So for experts, some special cases are the Tamal-Base equation or the Schlesinger system. Yeah.
Is there an easy way to see why this is nonlinear?
Why it's nonlinear? Well, and this thing is not really a vector bundle. It doesn't have any linear structure. It's just some algebra. I mean, this is just some affine algebraic variety. On this side, it's not affine. But yeah, I mean, being linear is some statement about maybe the total space is a vector bundle and some compatibility of the foliation with the GLN action on that vector bundle. In addition, here you just don't even have a negative structure to make sense of linearity. But in fact, it's sort of a theorem, I guess, going back to Penleve, but maybe made rigorous by Umemura, that like the typical solution to this ODE, to this differential equation, cannot be written in terms of solutions of linear differential equations. But Penleve called these solutions new transcendents, Penleve transcendents. I think that's somehow the history there. Okay, are there any questions about these examples?
Sorry, maybe it's basic question. So in your definition, the foliation is some subbundle, right?
Yes.
And what is the subbundle here?
Yeah, so I said it aloud what the leaves are, but from this point of view, it's pull it back from the tangent sheaf of this thing, and then it descends to the quotient. And then here I only just told you what the leaves are. So they're families of flat bundles whose monodromy representations are locally constant. Okay. But yeah, actually describing the foliation is a little complicated. I'll give you an example of it later. Thank you. Any other questions? Okay, so let me tell you what we can prove. And maybe I should say before I erase his name, everything I'm still talking about today is joint work with Josh Lam, who is on the job market right now. Okay. So let me start with some results. And I want to start with results for linear differential equations. So all of the results for linear and differential equations will be in this setting of Gauss-Monod connection. So what's the first one? So let me just say, we definitely do not know how to prove this for arbitrary Gauss-Monod connections, arbitrary solutions to arbitrary Gauss-Monod connections. In particular, that would imply the P-curvature conjecture for some ends of Gauss-Monod connections, which I mentioned earlier is very open. So already that case is going to be quite hard. So let me say what we do know how to prove Gauss-Monod connections. So let's see it. Smooth proper map with S smooth. And I want to consider the following flat vector bundle. So this is like a linear differential equation. And it's of this form 2 over here. I'm going to take 2k cohomology of x over s equipped with its Gauss-Monod connection. And now I pick this point. I want to pick an initial condition to take the Taylor, like a point to take the Taylor expansion of the solution to this differential equation around. So I want to take m in the fiber, which is just h2k of the fiber of f. I guess derived homology. And I want this to be in the image of the cycle class map. It's a map from cycles of codimension k on the fiber to this h2k from of the fiber. Then what's the theorem? So then the leaf through when m is algebraic, if and only if it's integral, so the formal leaf is integral, so that's this condition 2 here, and then if and only if this strong form I didn't write on the board in this case, but if you'd like, you can take S to be an open subset of the affine line, and then it's exactly this condition with omega p that I wrote down earlier. Okay, so the statement is that the conjecture is true in this case. But if you take the Taylor expansion to a Gauss-Monod connection at a cycle class. And maybe just let me stress, it's just a cycle class at one point. If you knew it was a cycle class everywhere, this would be trivial. And maybe let me just say for the experts, you don't really need that it's a cycle class, but you need is that it's a Hodge class and an absolute Tate class, meaning crystalline Frobenius acts on it like it would on the cycle class for infinitely many p in this case. Okay. So I'll try to say something at the very end about the proof of this, but maybe let me just say now the main input is the Maser-Ogus's theorem describing the interaction between crystalline Frobenius and the Hodge filtration model. Okay. Let me erase these examples and the conjecture up. Are there any questions about the theorem? No? Okay. Let me see what theorem B is. I like everything in the top. This is joint with Josh. So here I only proved something about quite special initial conditions, so points where you take the Taylor expansion of a solution around. So I wanted to include some results where, well, maybe where F is a bit special, but M can be arbitrary. So let me give you an example of such a result. So again, I'm going to look at a Gauss-Model connection, Picard-Fuchs equation. And so here I'm going to take X to S to be a smooth proper family of genus 1 curves. Like elliptic curves. And I want to take E nabla to be maybe symmetric power of the only interesting cohomology associated with this family. So the first from cohomology with the Gauss-Bonnet connection. And I want to take, so I fix a point in the base and I take an arbitrary initial condition. Okay, and then the theorem is that okay, the conjecture is true. So the leaf, so then the leaf through M is algebraic if and only if the formal leaf is integral, if and only if, well, the strong form holds. Okay. So maybe let me just say like that maybe this looks very special, but at least it covers some interesting cases. So for example, if you have a modular form associated to it is a solution to a Picard-Fuchs equation of this form. And so this says something about the Taylor expansions of the solutions to Picard-Fuchs equations associated to modular forms away from the cusps. And so I wanted to include this for a couple reasons. First of all, I think it's nice to have an example where you have an arbitrary point, but also, so a lot of the times modular forms have some kind of integrality properties when you expand them at the cusp. So for example, this elliptic integral I wrote down at the beginning of the talk had this integral Taylor expansion. And I was expanding it. You can interpret that as a statement about integrality of some modular form at a cusp. So this is showing that away from the cusp, at least, that example is okay. So in particular, it shows that that particular function I wrote down, if you take the Taylor expansion at any point which isn't 0 or 1, so any point where the ODE is non-singular, the conjecture is true. Maybe let me just say, like, you can actually really write down these differential equations pretty explicitly. So the flavor of this theorem is that you have some infinite sequence of Taylor coefficients, which are the solutions to some linear recurrence, and it says that infinitely many primes show up in their denominator. So it's really, if you can kind of translate this theorem, it's something you can explain to a high school student if you'd like. Great. So maybe let me just remark, this is not like an exhaustive list of the results we can prove for linear ODE. So for example, we can also do the same sort of thing for many second order ODE of geometric origin. So we don't quite know how to do arbitrary second order linear ODE of geometric origin, but I can tell you the things pulled back from Hilbert modular varieties basically we can handle. We can also handle things like with some reasonable notion of CM initial conditions. So for example, if you have a family of abelian varieties, you look at their first cohomology and take the Taylor expansion at a point where your family of abelian varieties is like a CM point, it's okay. And a few other cases, but I want to talk about nonlinear ODE now. Okay. So before I do that, are there any questions?
Or maybe you're going to talk about this, but you said in your proof of theorem A, like, what is it that allows you to handle this case but not some ends?
Yeah, I mean, it's somehow It's basically the case that the line spanned by these things are preserved by crystalline Frobenius. And so the summands are kind of permuted by crystalline Frobenius. It's somehow the same thing that if you run into kind of P-curvature conjecture for summands. Somehow you don't know that the Galois conjugate summands have any nice property. So for example, in the P-curvature conjecture, you don't know if they have vanishing P-curvature. Okay. Yeah, it's a good question. Great. Okay, so let me explain the theorem okay, maybe let me just say there is one more linear thing I did want to talk about. So I told you earlier that there's some predictions this conjecture makes about linear ODE that I don't know how to see from the P-curvature conjecture. We were able to check some of those predictions for hypergeometric functions. So if you'd like to hear about that, you can ask me that about it afterwards. Let me skip that and talk about nonlinear ODE. This is results for nonlinear ODE. Okay, and part of my goal for this last section of the talk is to try to convince you to care about nonlinear ODE, which I think is something that's maybe a little bit less familiar to the modal algebraic geometer. Okay, so let me remind you the settings. So this setting, so x to s, again, will be a smooth proper morphism of smooth C schemes, if you'd like. Again, you can equip this with a S and C divisor, but it makes things notationally more complicated, so I won't do it in the talk. And to this, we can associate this moduli space M theorem of x over s. And let me just say what its T points are. But its T points are, so here, T is an S scheme, so it maps to S, and the T points are flat bundles on xt over T. And if you'd like, you can decorate them with some extra data. So for example, I wrote SLR here, so these should be flat bundles with trivialized determinant. So this is some spec. I think it's a crystal on S, so I'm going to write this as carries a foliation, which I'll call F isomonodromy. And the analytic description of this foliation is that a leaf is a family of flat bundles whose monodromy representations are locally constant. The right way to say this is the crystal. Okay, before stating the theorem, let me give you an example. So unfortunately, the easiest example to write down is one which does have a normal crossings divisor. So I'm going to, even though I've been telling you that I don't want to do that, I'm going to do it in this case. So I want to take S to be the configuration space of n distinct points in P1. So if you'd like, you can think of this as ordered tuples, lambda 1 through lambda n, where lambda I is not equal to lambda j for all ij. And then over this, the x, which is just P1s, so P1 times s, but it will be equipped with a divisor, which is just the universal divisor over this point, so lambda 1 plus lambda n. This is the divisor h all over s. Okay. And in this case, M theorem will parameterize not just flat bundles, but flat bundles with regular singularities along the divisor. So, so what does a kind of generic flat bundle look like? It looks like, let's say, the trivial bundle on P1 with a connection of the following form: d plus sum of ai over z minus lambda I. Here this has regular singularities of lambda I, and let me just make the assumption that the sum of the ai is 0. So this just means that infinity is not one of the lambda i's. No singularity. Okay, then what does this isomonodromy foliation tell you? It tells you, as you vary lambda, how should you change A to keep the monodromy representation the same? And this was worked out by Schlesinger. So isomonodromy. So this was worked out by Schlesinger. Okay, let me move write it over here. Example continued. So Schlesinger in 1912 worked out that isomonodromy is given by the following. So I have to tell you how to change AI as I move lambda j. And the formula is dAI d lambda j is the commutator of AI with aj, or lambda I minus lambda j, I not equal to j. And then what you want this sum condition to stay true when you move the lambda I. So that just means dAI d lambda j is 0 for all. Okay, so if you want to figure out how to take the derivative of AI with respect to lambda j, you use that you know all but one of the sentences here. Okay, this is fun to work out. Maybe let me just remark. So in the case where n is 4 and the AI are 2x2 matrices, trace 0. This is the form of the Pendleman-6 equation. So you can do some change of coordinates to the Pendleman-6 equation. So this was worked out by Fuchs in 1905, I think, from more or less this point of view. Okay, so this is some very classical nonlinear differential equation. Maybe it's worth worth saying, since there's some people in this audience who have thought about this, people have been really interested in classifying algebraic solutions to this particular differential equation. So for example, the case where the AI are 2x2 matrices, the Pendleman-6 equation was, I think, arguably worked on since maybe the 1920s. And that case was just completed by combining work of myself with Lam and Lensman with very recent work of Bronstein and Murray. So we now completely understand algebraic solutions to this differential equation when the AI are 2x2 matrices. Great. Okay. So let me tell you the theorem in this case. So this is, I think I skipped theorem C, so this is theorem D. Again, it's joined with Lam. So I'm in this setting where I have a smooth proper X to S. If you'd like equipped with an S and C divisor, then I'll drop it from the notation. So it's the following. So I'm going to start with E nabla, which will be a flat bundle on one fiber, X sub S. And the assumption is that this is going to be a Gauss monodimension. What do I mean by that? I mean, there exists some smooth proper map to the fiber, so y to x sub s, to the fiber of this map. With E nabla, the cohomology of this map, or G lower star of y over xs, because it's Gauss monodimension. Then the theorem is that the following are equivalent. So if you'd like to have specified now a point of Enderon, and I'd now like to understand the algebraicity of the leaf through that point, and the theorem is that the following are equivalent, the leaf through this point, E nabla, and Enderon, X over S is algebraic. 2, the formal leaf is integral, and 3, strong. Okay, so luckily I've written these two theorems one underneath the other. I think you should really think of them as parallel. So this theorem D is the non-abelian version of theorem A. Okay, so that's the main result of the talk. So before I say a word in the last maybe 2 or 3 minutes about the proof, let me just make a remark on the relationship to the Picard-Fuchs conjecture. So this is some kind of proposition, which you can extract from a paper of myself with Brian Lawrence and this with Josh. So this main conjecture, so the conjecture above, for the isomonodromy foliation on M to ROM of the universal curve over MG, let's say to rank R bundles. So here I mean the moduli space of rank R flat bundles on the universal curve over MG implies the classical P-curvature conjecture. For rank R bundles on all brackets. So, I mean, of course, there's many kind of special cases that you can reduce the P-curvature conjecture to. Let me briefly make a pitch for this one, which is that this is some kind of non-abelian cohomology. It's a lot of extra structure. And so I think, you know, maybe a first thing to try to do is try to understand how to prove this for general initial conditions. But the point is that if you can prove this statement, not just for Gauss-Bonnet connections, but for arbitrary initial conditions, you've proven the P-curvature conjecture. So I'm not saying this is real progress towards the P-curvature conjecture, but at least it's a different point of view. All right. Are there any questions before I say a word about proofs? Do I have time, Bogdan?
I think 5 minutes.
So I'm not going to say anything about the proof of this theorem B, which was about families of genus 1 curves. You can ask me after if you want. But let me, so this is section 5 at the top, proof ideas. So I want to kind of in parallel describe the proof of theorem A and theorem D because they're very closely analogous. As I said, this is supposed to be the non-abelian version of theorem A. And so when you set up this, you start with a smooth proper morphism. Maybe let me just say again, this theorem is okay in the presence of an SMC divisor. The proof is quite a bit more complicated. Arguably, there are no new ideas. Okay, so let me say, draw some table to indicate the proof and say what the setup is. So here we have we start with some initial condition that we take the Taylor expansion of the solution to our differential equation round. In theorem A, it was M in the cohomology of a fiber, the cycle class. And in theorem D, it was a flat bundle on a fiber. It was a Gauss-Bonnet connection. Okay. So in both cases, this data comes with some extra structure. So in theorem A, M is a Hodge class. So M is in H2K, XS Q of I, intersected with HKK, like maybe the kth piece of the Hodge filtration if you want to be a bit more algebraic. And in theorem D, E nabla underlies a Z VHS, a Z variation of Hodge structure. Okay, so the main idea, it comes in 2 steps. So there's an algebraic step and an analytic step. So the algebraic step is to show that this structure extends to the formal leaf, so to the formal solution to our differential equation through this point. Here, what you need to show is that M tilde, this is the leaf, M tilde remains in the kth piece of the Hodge filtration. And to do this, one uses, as I said earlier, this Mazur-Ogus theory relating the Hodge filtration mod P to the crystalline turbines. In theorem D, you need to show that the Hodge filtration extends Griffiths transversely to the formal isomonodromy deformation. So the input, maybe I'll just write is, so the main input is Ogus-Woligodsky's non-abelian Hodge theory and characteristic P, and this theory of the Higgs-Duran flow developed by Sun Young-Fo. arguably there's some precursor unfolding. Okay, so in other words, in some sense, this flat bundle remains a variation of Hodge structure on the formal data. And then the analytic step, well, here one can use the polarization to show that the orbit of M under the monodromy action is compact and, well, it's discrete, so it's bounded. So here, arguably, the input is like the Hodge index theorem. Let me just say the polarization. And here, the input is, it's by fun, it's Deline's theorem on finiteness of the set of isomorphism classes of local systems carrying a ZVHS. Let me stop
Uh, questions to the speaker? So is there any formal relationship between theorems?
No, not as far as I know. But they're really, I don't know, this proof is like, it's not, I should say the preprint is not available yet. It's 99.9% written down. But this one is like 3 pages, this one is 30 pages, but except for that, they're line by line, sort of the same. And so each line becomes 10 times true. But yeah, so I would say there's a very close moral relationship, but no formal relationship. Yeah, all right.
In theorem A, is there some way that an odd degree cohomology you could prove some variance, like the images of Apple or Jacobi class maps or something?
Yeah, I started to think about this, but yeah, I don't yet know how to do it. I think, so first of all, I don't really see an algebraic foliation in the picture there. Like, of course, there's some kind of foliation on intermediate Jacobians, but it's sort of, I don't really know an algebraic way to make sense of it. Yeah, it's really tantalizing, but yeah, I don't know. I mean, of course, we're working very hard on trying to so for example, I would really like to get rid of this Q here and put a C here, and I think that's probably doable. There's lots of ways I think one could try to improve this theorem and get beyond cycle classes, but I think, I mean, as I said, like it's sort of closely related to the P-curvature conjecture for some ends, so you're not going to be able to get too much farther than this without some genuine new kind of algebra geometric input.
Can you say something about this proposition?
Sure, yeah, it's not very hard. So the idea is that, first of all, if you have a flat bundle with vanishing P-curvature, then the isomonodromic deformation satisfies condition 3 of this theorem. So that's pretty easy. The theorem predicts for you, sorry, the conjecture predicts for you that the leaf through it is algebraic. Another way of saying that is that the monodromy representation is finite orbit under the mapping class group. And now the idea is that the hypotheses of the Picard-Fuchs conjecture are stable under pullback. So you start with a flat bundle, let's say on a curve, you pull back to some really high genus curve, and then the conjecture tells you you get a flat bundle on that curve with whose monodromy representation is finite orbit under the mapping class group. And then Aaron Lansman and I showed that such things in finite monodromy once G is sufficiently big compared to the rank. Okay. Yeah. So strictly speaking, I didn't put Aaron up there, and it's because in an earlier work with Brian Lawrence, I showed that if you have a local system on a surface, and after all pullbacks, it has finite orbit with mapping class group, then it has finite monodromy. So if you just want this statement, it's a bit easier. Yeah, but so for example, what I just told you says something even stronger. It says, like, for example, if you prove this theorem for G is 4 and R is 2, then you've proven it for all rank 2 local systems on, let's say, smooth proper curves of genus at most 4. Yeah.
In theorem A, is there a relationship between this algebraicity of the leaf and this, M extending to a Hodge class?
Yeah, so that's a good question. So you could ask, like, yeah, what about just like, suppose you know the leaf is algebraic, does it stay a Hodge class? Maybe that's your question.
Yeah.
Yeah, so that follows from Deline's theorem of the fixed part. It's basically a statement of Deline's theorem of the fixed part for Hodge classes. Not such an easy theorem. So this actually gives a kind of different proof of that fact. It's kind of fun. Sorry, when the class is a cycle class, which is quite strong. So actually, one fun corollary of theorem D is that if you have a Picard-Fuchs equation, and its isomonodromic deformation is algebraic, then it stays a version of Hodge structure on all the nearby fibers. And that is kind of a deep theorem in the case of sort of general ZVHS of Picard-Fuchs in the case when S is proper, and then Josh Lam and Machizuki, and in very recent work of Kurtz when S is not proper. So this kind of gives an algebraic, or it's mostly algebraic proof of the same result. Yeah, so the Machizuki I mentioned is Dekuro Machizuki. So this, I think their argument really relies on the full force of non-abelian Hodge theory for like quasi-projective variety.
So you said this point of view led to consequences that weren't visible just from P-curvature.
Oh yeah, let me mention one of them. So I think the consequences are still conjectural, but we can check the conjecture sometime. So here's, let me call this a local conjecture. So everything I've said about this conjecture was at non-singular points, but let's think about what happens at a singular point. So let's suppose, if f of z is some n to the n with all, and suppose this is in the setting of the conjecture, so there's only finitely many primes dividing the denominators, and let's suppose this satisfies linear ODE with regular singularities at 0. Okay. So let's think about what the monodromy of 0 can look like. Well, if it is finite monodromy, you can pass to a ramified cover and get rid of the monodrome. And then the conjecture predicts that f of z is algebraic. Right? So then either one of two things has to be true. So one, f is algebraic, or two, let me give the ODE a name. df 0. So D has infinite monodromy. 0. So this I don't know how to see from the P-curvature conjecture, just because it's stated about one solution. And then maybe let me just say, actually, when I sort of realized this was a consequence of the conjecture, I was like, okay, the conjecture has to be false. It's like, I would have known this already if it was true. But it seems like it's true. So let me kind of say the proposition, and this comes from combining work of Kristall and Boykus-Heckman. Then maybe epsilon times Josh and myself, which is that this conjecture is true for hypergeometric functions. Yeah, Q. So this is, I mean, really just uses the Kristall classified hypergeometric functions of this form. Boykus-Heckman classified algebraic hypergeometric functions, and you compare the two classifications. So I think this is actually pretty strong evidence for the local conjecture.
Wait, then what's the epsilon?
Yeah, you have to do a little bit of Picard to understand. I mean, it's not, it really is epsilon. Yeah. Yeah, so at least this is some kind of prediction. I think it would be very interesting to prove this for Picard-Fuchs equations, and I'm kind of optimistic that one can do it.
Any other questions? Okay, if no questions, let's thank the speaker.